Hello everyone, it's Chloe from 19. It's day 14 in my challenge day, and today I'm going to learn some kind of primary tuning and regularization in the deep neural network, which is course second course in the specialization uh, specialization series. So let's start.
I've noticed that almost all the really good machine learning practitioners tend to have a very sophisticated understanding of bias and variance. Bias and variance is one of those concepts that's easy to learn but difficult to master. Even if you think you've seen the basic concepts of bias and variance, there's often more nuance to it than you'd expect. In the deep learning era, another trend is that there's been less discussion of what's called the bias variance trade-off. You might have heard of this thing called the bias variance trade-off. But in the deep learning era, there's less of a trade-off. So we still talk about bias, we still talk about variance, but we just talk less about the bias variance trade-off. Let's see what this means. Let's see a data set that looks like this. If you fit a straight line to the data, maybe you get a logistic regression fit to that. This is not a very good fit to the data, and so there's a concept of high bias, or we say that this is underfitting the data. On the opposite end, if you fit an incredibly complex classifier, maybe a deep neural network or a neural network with a lot of hidden units, maybe you can fit the data perfectly, but that doesn't look like a great fit either. So this is a classifier with high variance, and this is overfitting the data. And there might be some classifier in between with a medium level of complexity that maybe fits a curve like that. That looks like a much more reasonable fit to the data. And so that's the, maybe we call that just right, somewhere in between. So in a 2D example like this, with just two features, x1 and x2, you can plot the data and visualize bias and variance. In high-dimensional problems, you can't plot the data and visualize the decision boundary. Instead, there are a couple different metrics that we'll look at to try to understand bias and variance. So continuing our example of cat picture classification, where that's a positive example and that's a negative example, the two key numbers to look at to understand bias and variance will be the training set error and the dev set or the development set error. So for the sake of argument, let's say that recognizing cats in pictures is something that people can do nearly perfectly, right? And so let's say your training set error is 1%, and your dev set error is, for the sake of argument, let's say is 11%. So in this example, you're doing very well on the training set, but you're doing relatively poorly on the development set. So this looks like you might have overfit the training set, that somehow you're not generalizing well to this holdout cross validation set or the development set. And so if you have an example like this, we would say this has high variance. So by looking at the training set error and the development set error, you would be able to render a diagnosis of your algorithm having high variance. Now, let's say that you measure your training set and your dev set error, and you get a different result. Let's say that your training set error is 15%. I'm writing your training set error in the top row, and your dev set error is 16%. In this case, assuming that humans achieve, roughly 0% error, that humans can look at these pictures and just tell if it's a cat or not, then it looks like the algorithm is not even doing very well on the training set. So if it's not even fitting the training data as seen that well, then this is underfitting the data, and so this algorithm has high bias. But in contrast, it's actually generalizing at a reasonable level to the depth set, whereas performance of the depth set is only 1% worse than performance of the training set. So this algorithm has a problem of high bias because well, it's not even fitting the training set well. This is similar to the leftmost plot we had on the previous slide. Now, here's another example. Let's say that you have 15% training set error, so that's pretty high bias. But when you evaluate on a depth set, it does even worse. Maybe it does 30%. In this case, I would diagnose this algorithm as having high bias because it's not doing that well on the training set, and high variance. So this is really the worst of both worlds. And one last example, if you have 0.5 training set error and 1% depth set error, then well, maybe your users are quite happy that you have a CAD classifier with only 1% error. Then this would have low bias and low variance. One subtlety that I'll just briefly mention, but will leave to a later video to discuss in detail, is that this analysis is predicated on the assumption that human-level performance gets nearly 0% error, or more generally, that the optimal error, sometimes called Bayes error, so the Bayesian optimal error, is nearly 0%. I don't want to go into detail on this in this particular video, but it turns out that if the optimal error or the Bayes error were much higher, say it were 15%, then if you look at this classifier, 15% is actually perfectly reasonable for a training set, and you wouldn't say that's high bias, and it will also have pretty low variance. So you wouldn't say that's high bias, and it will also have pretty low 15 here, say it were in this particular video, but it turns out that if the optimal error or the Bayes error were much higher, say it were 15%, then if you look at this classifier, 15% is actually perfectly reasonable for a training set, and you wouldn't say that's high bias, and we also have pretty low variance. So the case of how to analyze bias and variance when no classifier can do very well, for example, if you have really blurry images so that even a human or just no system could possibly do very well, then maybe Bayes' error is much higher, and then there's some details to how this analysis would change. But leaving aside this subtlety for now, the takeaway is that by looking at your training set error, you can get a sense of how well you're fitting at least the training data, and so that tells you if you have a bias problem. And then looking at how much higher your error goes when you go from the training set to the depth set, that should give you a sense of how bad is the variance problem. So are you doing a good job generalizing from the training set to the depth set? That gives you a sense of your variance. All this is under the assumption that the Bayes error is quite small and that your train and your depth sets are drawn from the same distribution. If those assumptions are violated, there's a more sophisticated analysis you could do, which we'll talk about in the later video. Now, on the previous slide, you saw what high bias, high variance looks like, and I guess you had a sense of what a good classifier looks like. What does high bias and high variance looks like? It's kind of the worst of both worlds. So you remember we said that a classifier like this, a linear classifier, has high bias because it underfits the data. So this would be a classifier that is mostly linear and therefore underfits the data. I'm going to join this in purple. But if somehow your classifier does some weird things, then it's actually overfitting parts of the data as well. So the classifier that I drew in purple has both high bias and high variance. Right, that's high bias because by being a mostly linear classifier, it's just not fitting, this quadratic light shape that well. But by having too much flexibility in the middle, it somehow gets this example and this example overfits those. two examples as well. So this classifier kind of has high bias because it was mostly linear, but you needed maybe a curve function, a quadratic function, and it has high variance because it had too much flexibility to fit those two mislabeled or those outlier examples in the middle as well. In case this seems contrived, well, this example is a little bit contrived in 2 dimensions, but with very high dimensional inputs, you actually do get things with high bias in some regions and high variance in some regions. And so it is possible to get classifiers like this in high dimensional inputs that seem less contrived. So to summarize, you've seen how by looking at your algorithm's error on the training set and your algorithm's error on the depth set, you can try to diagnose whether it has a problem of high bias or high variance or maybe both or maybe neither. And depending on whether your algorithm suffers from bias or variance, it turns out that there are different things you could try. So in the next video, I want to present to you what I call a basic recipe for machine learning that lets you more systematically try to improve your algorithm depending on whether it has high bias or high variance issues. So let's go on to the next video. In a previous video, you saw how looking at training error and depth error can help you diagnose whether your algorithm has a bias or a variance problem or maybe both. It turns out that this information that lets you much more systematically, using what I call a basic recipe for machine learning, it lets you much more systematically go about improving your algorithm's performance. Let's take a look. When training a neural network, here's a basic recipe I would use. After having trained an initial model, I would first ask, does your algorithm have high bias? And so to try to evaluate if this algorithm have high bias. And so to try to evaluate if there's high bias, you should look at really the training set or the training data performance, right? And so if it does have high bias, so it's not even fitting the training set that well, some things you could try would be to try a bigger network, such as more hit layers or more hidden units, or you could train it longer, maybe run gradients and longer, or try some more advanced optimization algorithms, which we'll talk about later in this course. Or you could also try, this is kind of a, maybe it'll work, maybe it won't, but we'll see later that there are a lot of different neural network architectures, and maybe you can find a neural network architecture that's better suited for this problem. Putting this in parentheses, because one of those things that, you just have to try, maybe you can make it work, maybe not, whereas getting a bigger network almost always helps, and training longer, well, doesn't always help, but it certainly never hurts. But so when training a learning algorithm, I would try these things until I can at least get rid of the bias problems, as if go back after I've tried this until um, and keep doing that until I can at least fit the training set pretty well. And usually, if you have a big enough network, you should usually be able to fit the training data well, so long as there's a problem that is possible for someone to do, right? If an image is very blurry, it may be impossible to fit it, but if at least a human can do well on the task, if you think Bayes' error is not too high, then by training a big enough network, you should be able to hopefully do well, at least on the training set, to at least fit or overfit the training set. Once you've reduced bias to a acceptable amount, I would then ask, do you have a variance problem? And so to evaluate that, I would look at the depth set performance. Right? Are you able to generalize from a pretty good training set performance to having a pretty good depth set performance? And if you have high variance, well, best way to solve a high variance problem is to get more data. If you can get it, this can only help, um, but sometimes you can't get more data. Or you could try regularization, which we'll talk about in the next video, to try to reduce overfitting. And then also, again, this is sometimes you just have to try it. But if you can find a more appropriate neural network architecture, sometimes that can reduce your variance problem as well as reduce your bias problem. But how to do that, it's harder to be totally systematic in how you do that. But so I try these things and kind of keep going back until hopefully you find something with both low bias and low variance, whereupon you would be done. So a couple points to notice. First is that depending on whether you have high bias or high variance, the set of things you should try could be quite different. So I'll usually use the training depth set to try to diagnose if you have a bias or variance problem, and then use that to select the appropriate subset of things to try. So for example, if you actually have a high bias problem, getting more training data is actually not going to help, or at least it's not the most efficient thing to do. Right? So being clear on how much of a bias problem or variance problem or both can help you focus on selecting the most useful things to try. Second, in the earlier era of machine learning, there used to be a lot of discussion on what's called the bias-variance trade-off. And the reason for that was that for a lot of the things you could try, you could increase bias and reduce variance, or reduce bias and increase variance. But back in the pre-deep learning era, we didn't have many tools. We didn't have as many tools that just reduce bias or that just reduce variance without hurting the other one. But in the modern deep learning big data era, so long as you can keep training a bigger network and so long as you can keep getting more data, which isn't always the case for either of these, but if that's the case, then getting a bigger network almost always just reduces your bias without necessarily hurting your variance, so long as you regularize appropriately. And getting more data pretty much always reduces your variance and doesn't hurt your bias much. So what's really happened is that with these two steps, the ability to train a bigger network or get more data, we now have tools to drive down bias, and just drive down bias, or drive down variance and just drive down variance without really hurting the other thing that much. And I think this has been one of the big reasons that deep learning has been so useful for supervised learning, that there's much less of this trade-off where you have to carefully balance bias and variance, but sometimes you just have more options for reducing bias and reducing variance without necessarily increasing the other one. And in fact, so long as you have a well-regularized network, we'll talk about regularization starting from the next video, training a bigger network almost never hurts. And the main cost to training a neural network that's too big is just computational time, so long as you're regularizing. So I hope this gives you a sense of the basic structure of how to organize your machine learning problem to diagnose bias and variance and then try to select the right operation for you to make progress on your problem. One of the things I mentioned several times in the video is regularization. It's a very useful technique for reducing variance. There is a little bit of a bias variance trade-off when you use regularization. It might increase the bias a little bit, although often not too much if you have a huge enough network. But let's dive into more details in the next video so we can better understand how to apply regularization to your neural network. If you suspect your neural network is overfitting your data, that is, if you have a high variance problem, one of the first things you should try is probably regularization. The other way to access high variance is to get more training data. That's also quite reliable, but you can't always get more training data. It could be expensive to get more data, but adding regularization will often help to prevent overfitting or to reduce variance in your neural network. So let's see how regularization works. Let's develop these ideas using logistic regression. Recall that for logistic regression, you try to minimize the cost function j, which is defined as this cost function, sum over your training examples of the losses of the individual predictions and the different examples, where you recall that W and B in logistic regression are the parameters. So W is an x-dimensional parameter vector and B is a real number. And so to add regularization to logistic regression, what you do is add to it this thing, lambda, which is called the regularization parameter. Say more about that in a second, but lambda over 2m times the norm of w squared. So here, the norm of w squared is just equal to sum from j equals 1 to nx of wj squared, or this can also be written w transpose w is just a squared Euclidean norm of the parameter vector w. And this is called L2 regularization, because here you're using the Euclidean norm, also called the L2 norm of the parameter vector w. Now, why do we regularize just the parameter w? Why don't we add something here, about b as well? In practice, you could do this, but I usually just omit this, because if you look at your parameters, w is usually a pretty high dimensional parameter vector, especially with a high variance problem. Maybe w just has a lot of parameters, so you're fitting all the parameters well, whereas b is just a single number. So almost all the parameters are in w rather than b, and if you add this last term, in practice it won't make much of a difference because b is just one parameter out of a very large number of parameters. In practice, I usually just don't bother. Almost all the high b value. Now, and this thing, lambda, which is called the regularization parameter. Say more about that in a second. But lambda over 2m times the norm of w squared. So here, the norm of w squared is just equal to sum from j equals 1 to nx of wj squared, or this can also be written w transpose w is just a squared Euclidean norm of the parameter vector w. And this is called L2 regularization, because here you're using the Euclidean norm, also called the L2 norm of the parameter vector w. Now, why do we regularize just the parameter w? Why don't we add something here, about b as well? In practice, you could do this, but I usually just omit this, because if you look at your parameters, w is usually a pretty high dimensional parameter vector, especially with a high variance problem. Maybe w just has a lot of parameters, so you aren't fitting all the parameters well, whereas b is just a single number. So almost all the parameters are in w rather than b, and if you add this last term, in practice it won't make much of a difference, because b is just one parameter out of a very large number of parameters. In practice, I usually just don't bother to include it, but you can if you want. So L2 regularization is the most common type of regularization. You might have also heard of some people talk about L1 regularization, and that's when you add, instead of this L2 norm, you instead add a term that is lambda over m of sum over of this. And this is also called the L1 norm of the parameter vector w. So a little subscript 1 down there. Right? And I guess whether you put m or 2m in the denominator, it's just a scaling constant. If you use L1 regularization, then w will end up being sparse. And what that means is that the w vector will have a lot of zeros in it. And some people say that this can help with compressing the model, because if some parameters are 0, then you need less memory to store the model. Although I find that in practice, L1 regularization to make your model sparse helps only a little bit. So I don't think it's used that much, at least not for the purpose of compressing your model. And when people train neural networks, L2 regularization is just used much, much more often. Oh, sorry, fixing up some of the notation here. So one last detail, lambda here is called the regularization parameter. And usually you set this using your development set, or using holdout cross validation, where you try a variety of values and see what does the best in terms of trading off between doing well in your training set versus also setting the two norm of your parameters to be small, which helps prevent overfitting. So lambda is another hyperparameter that you might have to tune. And by the way, for the programming exercises, lambda is a reserved keyword in the Python programming language. So in the programming exercise, we'll have LAMBD without the A, so as not to clash with a reserved keyword in Python. So we use LAMBD to represent the lambda regularization parameter. So this is how you implement L2 regularization for logistic regression. How about a neural network? In a neural network, you have a cost function that's a function of all of your parameters, W1, B1 through W capital L, B capital L, where capital L is the number of layers in your neural network. And so the cost function is this, sum of the losses, summed over your M training examples. And so to add regularization, you add lambda over 2m of sum over all of your parameter w, your parameter matrix is w, of their, let's call it the squared norm, where this norm of a matrix, really the squared norm, is defined as the sum over I, sum over j of each of the elements of that matrix squared. And if you want the indices of the summation, this is sum from I equals 1 through nl minus 1, sum from j equals 1 through nl, because W is a nl by n L minus 1 dimensional matrix, where these are the number of hidden units or number of units in layers L minus 1 and layer L. So this matrix norm, it turns out, is called the Frobenius norm of a matrix, denoted with F in the subscript. So for arcane linear algebra technical reasons, this is not called the L2 norm of a matrix. Instead, it's called the Frobenius norm of a matrix. I know it sounds like it'd be more natural just call the L2 norm of the matrix, but for really arcane reasons that you don't need to know, by convention, this is called the Frobenius norm, which just means the sum squared of elements of a matrix. matrix. So how do you implement gradient descent with this? Previously, we would compute dw, using backprop, where backprop would give us the partial derivative of j with respect to w, or well, really w for any given L. And then you update WL as WL minus the learning rate times D. So this was before we added this extra regularization term to the objective. Now that we've added this regularization term to the objective, what you do is you take dw and you add to it lambda over m times w. And then you just compute this update same as before. And it turns out that with this new definition of dwl, this is still, this new dwl is still a correct definition of the derivative of your cost function with respect to your parameters, now that you've added the extra regularization term at the end. And it's for this reason that L2 regularization is sometimes also called weight decay. So if I take this definition of dwl and just plug it in here, then you see that the update is WL gets updated as WL times the learning rate alpha times the thing from backprop plus lambda over m times WL, so with a minus sign there. And so this is equal to WL minus alpha lambda over m times WL minus alpha times the thing you got from backprop. And so this term shows that whatever the matrix WL is, you're going to make it a little bit smaller, right? This is actually as if you're taking the matrix W and you're multiplying it by 1 minus alpha lambda over m. You're really taking the matrix W and subtracting alpha lambda over m times it. So it's like you're multiplying the matrix W by this number, which is going to be a little bit less than 1. So this is why L2 norm regularization is also called weight decay, because it's just like the ordinary gradient descent, where you update W by subtracting alpha times the original gradient you got from backprop, but now you're also, multiplying W by this thing, which is a little bit less than 1. So So the alternative name for L2 regularization is weight decay. I'm not really going to use that name, but the intuition for why it's called weight decay is that this first term here is equal to this. So you're just multiplying the weight matrix by a number slightly less than 1. So So that's how you implement L2 regularization in a neural network. Now, one question that people sometimes ask me is, hey Andrew, why does regularization prevent overfitting? Let's take a quick look at the next video and gain some intuition for how regularization prevents overfitting.
Okay, before I go to end up this recording, I just do I'm just going to do short that first. So today I learned how to set up ML application in this course, and to build a machine learning application, we need to set up this kind of parameters like number of layers, the number of hidden units, and learning rates and activation functions. And also we have to partitioning we have to partition uh, a set of data set into separate classes, which is training set and that development set and test set. We use training set for to train model based on the training inputs, and we use a development set for cross validation. And after that, we use test sets to test actual result by comparing the output and with the true label. And the output is equal to prediction from our model. There is some kind of traditional rule in machine learning field, which is 7 versus 3 ratio, and this is 2 in general. To partitioning our data sets. And professor gives us a few advices that make sure that data set and test set come from same distribution, because it may lead to a faster learning algorithms. And it might be okay not to have test sets if we don't need unbiased estimate. The next topic is about bias and variance in neural networks. For example, when we do a classify uh, an image to to determine that whether the image is about cat or not. About this problem, human has roughly zero error. Uh, all of training samples, but about the machine, we can think of the few different cases. There is a case only high variance, and after the the second is high bias, and third is high variance and high bias at the same time. And finally, low variance and low bias, which is the best case that we can satisfy our users. And for each cases, I depict the situation in the paragraphs. And for each problems that high variance and high bias, and we can follow some basic recipe for machine learning. If our algorithm has high variance, we can try a bigger network and training longer, or try different NN architectures. Then after that, if our algorithm ensure that there is no high variance, we can, oh, sorry, it's bias. We can try, then we can assure a question that if whether our algorithm has high bias or not. If yes, we can try more data or regularization and different NN architecture at the same time. Then go to the first step again, and we validate our approach about the train set or test sets. And the things that we should try to do in for each of problems is can be different, because For example, trying more data in improvement of high bias may not be helpful in this case. So we need to keep in mind that we need different things for improving different problems. And additionally, in the modern era of deep learning, we can improve the one one problem among bias and variance problem without hurting much performance of the other. The next topic is regularization, and I'm going to recap this after finishing whole sectors. So thanks for your watching.